What's up guys, this is Geeta Thakur. Today we are going to be talking about class 10 science chapter. We are going to be talking about the periodic table. Now the periodic table is an amazing contribution to science. It's the thoughts of a lot of scientists, and what they've done together, they tried to catalog all the elements, they tried to explain the properties, and not only were they successful at doing that, actually they did it so well that the periodic table actually predicted a few elements that we hadn't found. It told us about properties of these elements. It told us what are the compounds that can be formed, how are these compounds formed, what elements react with what elements. It basically gave us all insight into matter. It gave us insight into everything that you see, you touch, you feel. So this is really an amazing testament to how science works. So let's get started. Let's see how we begin. The first step in our journey is actually knowing what elements is. The idea of elements is a really old one. It goes back to 330 BC. Plato, he said that there are 4 elements and everything is made up of these 4 elements. There was earth, fire, wind and water. Now, these were the 4 elements according to the Greek, but there were some substances that we could not break down into simpler substances. We heated this and we actually used all of this stuff a lot. So we had a few metals. We had copper, zinc, silver, mercury, gold. We had a few non-metals. We had sulfur and carbon. And then again, we had a few metals. These metals over here actually were easy to find. These ones were a little difficult and we found them later. So we had lead, we have antimony over here, we have arsenic. These were the metals we knew for a really long time. We could not break them into simpler substances, no matter how much energy we provided to them. All right, so now after about 2000 years, in the year 1609, we have Henning Brand. He was an alchemist. What he was trying to do is find the philosopher's stone, which basically is he was trying to find this mythical substance, and if it touches any inexpensive metal, it turns it to gold. And what he did for that is he figured urine is gold, and if I heat up a lot of my urine, maybe I can find this philosopher's stone. So he collected lots and lots of urine. He aged it till it started really stinking. And then his process was to heat this up. He heated it up till he got this white paste, okay? And then when he wanted to do experiments on the white paste, he realized that it just burned. So that was the first time we found an element. We heated a compound so much that it broke down into the simpler stuff that it was made up of. What Brand had discovered was actually white phosphorus. Phosphorus, it glue in the dark, and when exposed to air, it instantly caught fire. Phosphorus means light bearer because it glue, that's what he called it. We actually have white phosphorus, which is extremely reactive, and then we have another kind of phosphorus. We have red phosphorus. Now this is what you find on the head of matchsticks. And it's also quite reactive. Just a little bit of friction is enough to get the flame going. And white phosphorus is a lot more reactive than that. It does not even need the flame to get it going. We also have another allotrope, which is black phosphorus, but that's not so reactive and we don't use it at a lot of places. Well, what happens next over here? We have Antoine Lavoisier. Now this guy is known as the father of modern chemistry. He revolutionized chemistry. Before him, it was just alchemy. Scientists were just mixing stuff, seeing what happens. There wasn't a lot of thought to it. He wrote his elementary textbook of chemistry, in which he actually defines what an element is. He says that an element is a simple substance that cannot be broken down by chemical process. By giving it heat, actually, is what we believe, by giving it some energy. He had 33 elements that he had classified. We had metals, we had non-metals that he had classified, we had gases. Now if you see on the gas, he also classified light and heat. At those times they were believed to be elements. And over here we have some compounds that are found in earth. We call them minerals today. So we have calcium oxide, we have oxides, and because he couldn't break them down into simpler substances, he believed these were elements too. He gave us this classification. Now let me tell you what's so great about what Lavoisier did. He theorized, a lot of scientists believe that there was phlogiston. Now that is something that each material, each thing that burned had in it. It was an intrinsic quality. He said, no, that's not true. Things burn because they're in an atmosphere of oxygen. His careful weighing of the elements and weighing of the reactions is what helped him show this, is what helped him prove it to the world. He weighed wood and he found that the mass that the wood lost and it became ash, this mass was actually there in the carbon dioxide, in the gas that was formed when it was burning. And he said he believed that it was oxygen that was responsible for burning and not phlogiston. So that is what Lavoisier did. Let's see who's next. We have Dalton. So in 1808, Dalton published his theory of what an atom is. That was the first time the word atom was actually given a meaningful definition. The word was coined before, but Dalton gave it all these properties. It said that an atom of a particular kind is going to have the same properties. An oxygen atom is going to be an oxygen atom always. It has similar physical properties. It's going to have the same mass. It's going to combine with other compounds in a specific ratio. According to him, we had one oxygen and one hydrogen to give you one molecule of water. That is what he believed. One nitrogen will combine with exactly one molecule of hydrogen to give you ammonia. Now, get this, he did not know the atomic weights of these. He did not know in what proportion they combine, but he had a good enough sense. He gave water enough energy for it to break. He studied the gases that were coming out of it. He weighed the gases that were coming out of it. And then he made estimates as to what is actually happening. So the mass of water is broken down into oxygen and hydrogen. How much oxygen and how much hydrogen? This was basically done by conservation of mass, which was given to us by Lavoisier. He said, according to him, one carbon will combine with two oxygens to give you carbonic acid. One sulfur will always combine with three oxygens and one more oxygen to give you sulfuric acid. So he told us that elements combine in a fixed ratio, they have properties, and the greatest thing about the greatest contribution of his to the periodic table is atomic mass. He said there is something as an atomic mass. All elements have this and they have a fixed atomic mass. So the hunt to actually classify, to understand elements, to know what's happening to them is still going on. We don't really understand. So we have Dobereiner's triads. Let's see what he did. What he did was he tried to find elements that shared a property. So for example, we have lithium, sodium and potassium over here. They were all extremely reactive. They reacted with water and they gave us extremely basic oxides. He sees lithium, sodium, potassium, and he sees that their atomic weights are 7, 23 and 40. And 23 is the mean of 7 and 40. It's somewhere, it's the average of 7 and 40. He didn't just see one such triad. He saw chlorine, bromine and iodine. All of these are halogens. They react very aggressively with the metals, with these metals, and they also seemed to share the same property, the atomic mass of the one in center. So the atomic mass of bromine is 80, which is the average of the atomic mass of chlorine and iodine. So what he did was he actually related the properties and the atomic mass. He came up with a law that the atomic mass of three elements grouped together with similar properties, the average of the first and the last one gives you the second one, approximately the second one. So he did the same thing with lithium, sodium and potassium. And these formed the Dobereiner's triads. These formed the triads. He also spotted another one, which was calcium. We have 40 and 137, which is 177, strontium and barium. But there are more such triads. So there was beryllium, magnesium and calcium, which also forms a triad. We have sulfur, cesium and tellurium. They also form a triad. They also form a Dobereiner triad. But these were not the triads that he found. So that's what he did. He actually was the first guy to show that atomic masses were somehow related to the properties. There was something about the atomic masses. When you take the average, you also get the average of properties. So there was something going on over there. Now he just gave us 3 triads, but this did not help us understand all the other elements over here. This did not help us understand what else is going on. If you do form a triad, you understand, okay, the 3 of them have similar properties. But it wasn't very useful to predict how elements would behave. I actually wanted to tell you about why we can only come up with some triads and not so many more. It's because not all the periods have equal number of elements. So for example, if you'd assume that these 3 are a triad, they're not, because between cobalt and rhodium we have actually 17 elements, all of these. But between rhodium and iridium we don't have 17, we have 17 plus 14, which is about 31 elements. We have all of these, and then we have the lanthanide series. So that's a lot of elements between this last 2, and iridium is a lot heavier than rhodium. So rhodium is more towards the weight of cobalt, and it's not really in between. So we have some of these triads. Remember, he was the first guy to relate atomic mass and the characteristics. But as the classification goes, it wasn't very helpful. We just had some triads. It gave us an idea of what is happening with some of the elements, but not with all of the others that were discovered back then. All right, let's go to our next guy. Our next guy is Newlin. Now Newlin introduced the word periodicity. What he said is he gave us octaves. He compared elements to the tones, the music tones. So we have do, re, mi, fa, sol, la, ti and do again. So what he did was he was telling us that all of the elements over here, the 8th element after the first one, or if I count from here, the 8th element from here after 8 elements, all of these have the same properties. So when you arrange them in sets of 7, the next element over here is going to have the same property as the previous one over there. He gave us the word periodicity, and this was a great way to understand elements, but there were a lot of drawbacks over here. So for one, if he could not, like, we had potassium and copper that did not really share the same properties. So this sort of lost its the trend. All of the periods, it wasn't really belonging. It was perfect up to calcium, but after calcium they were not really exactly following the same properties. He force fitted some elements. Over here he's put 2 instead of putting 1. There were a lot of problems. He had 56 elements, and he said that there were no more elements. We were done with finding the elements, but of course we found a lot more elements. As we know it, Newlin's octave did not really work very well, and we had to let go of that theory. But it worked till calcium. Okay, so that is what Newlin's octaves were good till calcium. Then we have our next guy. So the next guy we have is Mendeleev. Now let's see what Mendeleev did. Okay, he arranged he took cards and he wrote down the properties of each and every element. He arranged them by atomic mass, okay, by an increasing order of atomic mass. So he had a stack of cards which went like hydrogen, then lithium, then beryllium, then boron. Okay, now let's say he started with lithium. Okay, it's an easier place to start with than hydrogen, so we start with lithium. So he places the first one over here. Next, beryllium goes over here. Next, boron in the next group, carbon in the next group, and he goes on doing this till he gets to sodium. Now, instead of placing sodium right after fluorine, he sees that sodium's properties, its chemical properties, are very close to lithium. So instead of placing it here, he puts it down over here. And then he continues, magnesium goes here, aluminum goes over here. And as he does this, he realizes that the two elements that he's putting in one group, they have the same properties. Now, what Newlin did was switch on every 8th element. Mendeleev didn't think that was important. What he thought was important is just to get the properties in one group. So in the next time he did that, after chlorine, when he goes to potassium and then he has calcium, over here, he does not even have an element. He's like, you know what, I cannot find any element that shares its properties with boron and aluminum. So I'm going to leave that. I'm going to leave that as a space. Titanium, it makes a lot more sense for titanium, the next element that was known, to go with carbon and silicon. And that's what he did. He left a group. He paid a lot of attention on the properties of the element and not so much on the atomic mass. That was not the most crucial thing in his periodic table. Now, the genius of Mendeleev was actually to leave these gaps, okay? It was to leave these gaps. He said that these elements are not known yet and we are going to discover them in the future. He called these elements, so there was Eka-boron, there was Eka-aluminium and Eka-silicon. Eka-aluminium, according to him, had a low melting point because aluminum did. Aluminum forms Al2O3, and he said Eka aluminium would form E2O3. It would combine with oxygen in the same ratio. And when we found gallium, sure enough, everything that he had predicted, the density, the boiling point of the melting point of the metal, and all its chemical properties were exactly as Mendeleev predicted. So this gave us a lot of faith in his periodic table. So that was the genius of Mendeleev's periodic table, but there were still a few problems with this periodic table. So if we are going according to atomic mass, what do you do with isotopes? Now, what are isotopes? Isotopes are elements, two different types of the same element. So we can have an isotope. We have 3 isotopes of hydrogen. One of them weighs 1 atomic mass unit, the other one weighs 2, and the other one weighs 3. Now, if you are categorizing your elements by atomic mass units, you should ideally have 1, 2, 3. But for him, hydrogen had just 1 block because it had all the same properties. So he wasn't strictly sticking to atomic mass. Over here, we have cobalt and nickel. Cobalt was actually heavier than nickel, but he switched them because the properties made a lot more sense. So he stuck to the properties, and that's what he did. He kept gaps in his periodic table, and it exactly lined up with his predictions of what the element would be like. So that was the genius of Mendeleev's periodic table. But like we discussed, there were 2 limitations. 1, he could not fit in isotopes. 2, the mass numbers were always not in order. Now, when this is back when noble gases were not discovered. We did not know any of the noble gases. So, but when we started discovering noble gases, their properties weren't shared with any of these elements. So we actually started a whole new group, and as we discovered more and more of them, they just went down over here. So that was also beautiful because the noble gases just fit into his periodic table without changing anything at all. So now I keep saying that Mendeleev really paid attention to chemical property. What chemical properties are these? He really focused on how these elements combined with hydrogen and how they combine with oxygen. Hydrogen and oxygen are both very reactive. How many molecules of each element does it take to combine with one of hydrogen and one of oxygen? And that was the main property that he focused on while he was making his periodic table. All right, let's see the next one over here. The next periodic table is the one that we have today. This was presented to us by Henry Mosley. He just made one minor change in Mendeleev's periodic table. Instead of atomic masses, he told us that it is the atomic number that determines properties of an element. Atomic number is the number of protons in the nucleus. It's the number of electrons that an atom has. So, and that's how he arranged it. So right here we have the atomic number 1. Hydrogen has 1 electron, it has 1 proton. we have helium with atomic number 2, we have number 3, number 4, 5, 6, 7, 8, 9, 10. As we go towards the right, we keep adding electrons. As we go down below, we're going to add an entire shell. It's like adding a whole new bus for more of the electrons to be seated in. This was what Mosley did. It was one change, but everything fell into place now. There were no exceptions except where hydrogen should be placed. Hydrogen is a non-metal, but it's placed with the metals. That is still a drawback of the modern periodic table. Maybe you can figure out how to fix that, what is the best place for us to put hydrogen. Now, let me explain this periodic table to you a little bit, okay? These vertical rows are known as the groups. They are a group because they share the same properties. All of these share the same properties. And then as we move across a group, like I said, keep in mind we are adding an electron as we go towards the right. As we go down, these are periods. So this is an entire period. Now what is a period, Mark? I have the first period, second period, third period, fourth period. In the fourth period, I have 4 shells. In the fifth period, I have 5 shells being occupied. In the sixth period, I have 6 shells being occupied. And that gives us the period. Now, if you look over here, we have the extremely reactive metals. These metals are extremely reactive. You will not usually find them just lying about. You have to extract these metals because they have already reacted with something in the earth. These are known as alkali metals. They react with water. These are known as alkali earth metals because these are minerals that we find in the earth's surfaces. That's how they get their name. These are known as the transition metals. All of these over here are the transition metals. Over here, the green ones over here, we have non-metals. And if you see this step over here, if I just draw a line from boron, these are the metalloids. They share their properties. They are between the metals and the non-metals. As you can see, we have a lot of metals in the periodic table. Over here, I want to tell you metals, what they want to really do is they want to give their electron. Okay, we are going to get into why they do that, but these over here, they really want to give their electron away, and over here, they want to accept. They want to take, they want to get the electrons. Okay, now let me show this to you. This is actually the periodic table that we refer to. Right, it's got this whole other list of elements right here. These are the lanthanides and the actinides, right? So we have 2 more types of elements over here. We have the lanthanides, the actinides, the transition elements. We have non-metals over here. We have halogens, and we have the inert gases in this group. But of course, this is too difficult to represent on a page. Our pages are not usually so long. So we fold this up. And what we have is we represent it over here. So the first period over here has just 2 elements. It's known as a very short period. It's the shortest period. We have just 2 elements. The next period we have 8 elements. Again, we have 8 elements. Next, we have 18 elements in the 4th period because we have 10 transition metals. Again, in the 5th period, we have 18 elements. In the 6th period, we have all 18 of these, and then we have the 14 lanthanides, which gives us 32 elements. And the 7th period is 32 elements as of now, but we are still discovering elements. We are still synthesizing elements. We are at this position where we are making elements. We don't even find them in the Earth's crust. We bombard particles and we try to make new elements. And so the periodic table is not complete because we keep making new elements. And so the 7th one, as of now, as of today, we have 32 elements, but hopefully we'll find a lot more in the future. That's it. That's basically about how the periodic table is arranged, why it is such a beautiful arrangement, and what does it actually explain is what we are going to get into next. So guys, those are the periodic table. We did Dalton's elements, we did Lavoisier's periodic table of elements. We learned about how Dobereiner arranged his triads. We learned about Newlin's octaves, and finally we learned about Mendeleev, and finally we came to the modern periodic table, which is by Henry Mosley, which is determined on atomic number, the number of electrons. Electrons are extremely extremely important. We're going to understand how important, and we're going to understand how do the electrons change their behavior as we move across a group or as we go down a period in the next video. In the next video, we're going to be talking about valencies, about the periodic trends, about what is happening to these elements and why this is such a beautiful way to classify it, why it gives you a snapshot of everything that elements do, why it can help us understand all the matter that exists in the universe. So I am so excited for that video. I hope you are too. Please give this one a thumbs up, and if you enjoyed watching, please share it with your friends, and please put in any questions that you have about the video. I will be glad to answer them, and I will see you next time. Take care.